In this video, we're going to talk about what the normal distribution is and why it's so important to statistics. So the normal distribution is a probability distribution. So like other probability distributions, it's going to have values along the horizontal axis and probabilities along the vertical axis. So this is going to be probabilities. Probability of each one of those values. Current. And right here in the middle, this is going to be the average. Going to be the average of the values. So if we're talking about a random variable here, this area right in the middle of the normal distribution is going to be the average for that random variable. So the normal distribution is always going to look like this. It's often called a bell curve because it has this particular shape. And obviously the average comes right in the middle at sort of the top of the highest point, meaning it's got the most probability associated with it, and most of the values for that random variable are going to fall pretty close to the average, right around here. The bulk of the area of the curve, meaning the bulk of the probabilities associated with the values, are going to be clustered around the average. You've also got an even distribution of values, or an even distribution of probability to the left and the right of the mean. And there's very little probability associated with the outliers. So the farther you get away from the average of that random variable, the less likely you are to see those values. So values that are much less than the average or much greater than the average are a lot less probable. The normal distribution is key because it comes up all the time. It happens very, very frequently in nature, for instance, and we're going to talk about scenarios in which the normal distribution applies. But let's first of all take a look at an example. In fact, we're going to use the example that we talked about in the last video, which is you're throwing a surprise birthday party for your friend Jim. And in this scenario, we said you're trying to throw the birthday party at 4 p.m., and actually, let's just say you told your friend Jim that he should arrive at 4:15. So in the last scenario, I said that Jim was very unpredictable. I said that he might arrive any time between 3:45 and 4:45. But let's say that Jim's behavior is he's actually a pretty reliable guy. And so if you tell him to arrive at 4:15, he's probably going to arrive sometime around 4:15. This is actually a far more likely scenario. That is, the guy's more likely to arrive around 4:15 than some outlier, some time that's far away from 4:15. This is the way most people, in fact, act. There's still a chance he might arrive, a half hour earlier or a half hour later, but it's less likely. So our probability distribution for Jim's arrival time might look something like this. Here we have the value for. We told him to arrive at 4:15 because we needed about 15 minutes to get set up. And we were told everyone else to arrive at 4, so we said, Jim, you arrive at 4:15. And his actual arrival time might look something like this. Between 3:45 being fairly unlikely and 4:45 also equally unlikely. Most likely, the guy's going to arrive around 4:15 when we told him to. Now, you might say this is actually somewhat unrealistic. Most people tend to arrive later than we tell them to. Okay, but just bear with me here. This is a more likely scenario. Maybe 4:15 is not really the average. Maybe it's something like 4:20 if he's like a lot of people who tend to arrive on average about 5 minutes late. But the distribution for his arrival times is much more likely to look like a normal curve, much more likely to look like a bell curve, in that he's likely to arrive sometime around a specific time. The average of his time might not actually be 4:15, it might be 4:20 like we said, but there's going to be a clustering around that average for the random variable, and there's a possibility of other times his arrival times being some significantly earlier or later, but they're a lot less likely. And so this would be a good probability distribution around Jim's predicted arrival time. So let's look at another example of where a normal probability distribution might come up. Let's say we've created a histogram of average age of students in an incoming MBA class, a full-time MBA class. So here I've got a histogram showing the probability distributions for students' ages. So if we have an incoming class of, I don't know, 300 students, we might have an average age of 28 years, so there's a lot of students who are 28, and if we have a standard deviation of something like 3 years, or let's say 2.5 years, we might have a histogram of probabilities that looks something like this. Now, if you add up all of the areas of these rectangles, of the bars, you're going to get 1. They're going to all add up to 1. So this is all the ages in an MBA class. We'll say everybody's between 22 and 34 years. That's probably not true to life, but for this simplicity, to have a simple result here, this is our histogram. Everybody's between 22 and 34, and you have a whole lot more 28-year-olds, 27-year-olds, 29-year-olds than you do 34 and 22-year-olds, for instance. Now, we might actually graph this. With an MBA class of 300, it might actually look something like this. Notice it's not exact. Our bars on either side. This doesn't. There's actually more 29-year-olds than there are 27-year-olds. Big deal. If we had a really big population that we're dealing with, say like all MBA students anywhere, all full-time MBA students starting at programs across the country, we wouldn't have. Our graph would be a lot smoother. We might have a line that looked something like this. Well, that was not the smooth line I could have drawn. But we might have something that looks like this. And this is the normal distribution. It's a bell curve, because we're going to smooth out these edges. We're going to say, especially if what we really, this is what we really need, is to say not just designating ages by exact numbers, but if we designated them by days. So if we said anything between 22, we have 365 data points between 22 years old and 23 years old, and between 23 years old and 24 years old. Well, then it's not going to look like this bumpy histogram. It's going to look like a curve. And so if we took all the students in the United States and we graphed them out by the number of days old they are, it's going to look something like this. It's going to be a nice smooth bell curve, presumably. The bell curve comes up a heck of a lot in Nation. One of the places that it comes up a lot, and this is good information for you, particularly and this is going to sort of make things are going to start making sense now when we've been talking about standard deviations, is test scores. So typically, this isn't always the case when students take a test, but typically you start to see a bell-shaped distribution of students' test scores in a class, meaning a lot of students are going to be clustered around the mean. There's going to be, if the average is 85, you're going to see a lot of students right around there, in the 80s. And then there's going to be a couple of students who really flubbed it, or in the 40s, and you're going to see, a few more students up near 100. So that's usually the case. It's certainly the case with most standardized tests like the SAT, the GMAT, MCAT, and all those big standardized tests are going to have a normal distribution around them. So let's take a look at a sample that I'm going to do in Excel here. So I've actually got 78 students' test scores. These are not real test scores. I made them up. And like most test scores, these are going to follow roughly a normal distribution. So we've got an average, which I took actually all 78 test scores. They're all in column B. You can see there's 78 of them. Their average, according to the function here, is going to be 82. And their standard deviation is 6. So average of 82, standard deviation of 6. Let's look at a histogram of all test scores in this class. This is it. We have many different possibilities we have lowest test score is 67. There's only one of them. This is, notice, a histogram of the frequency, not of the probability. But the truth is, the proportions are going to be the exact same. So if we turn this into probabilities, we would also get the exact same look on the in terms of the size of each of these bars. So, I mean, we would just take each of these values divided by 78, and we'd still get the same proportion, the same heights. This doesn't look really good in terms of a normal distribution. And when you have a small sample size, that's often the case. You're not going to have an exact. So 78 is, it's a reasonable sample size. But if we had, say, 7,800 students, we'd be much more likely to see a smoother distribution. I did go ahead and I broke this down actually, and I grouped the group the scores into ranges of 3, because it's sort of funny seeing we have 30 possible values here, and it sort of makes things hard to read. But if we group them into 3s, so everybody who scored below a 68, and then between 68 and 71, and 71 to 74, now this is starting to look a lot more like a normal distribution. Oops. Sloppy normal distribution, as I write it. But you can see this is sort of how things happen very often. Many times in nature, and you'll see with sampling all the time, you're going to have a normal distribution formed. So we're going to talk about that more in a moment. Before we go into more examples of normal distributions, however, I want to talk about some of the properties of the normal distribution. So one thing I want to point out first of all is that when we're talking about normal distributions, they can look like this. Okay, that's pretty bad, but they can look like that. Or they can look like this. Meaning, it doesn't really matter how wide or high the normal distribution is, so long as they have to have several basic properties. The average of the random variable has to be in the middle, and we have to have a basically even distribution of results and probabilities on either side. Of course, this is a probability distribution, so the area underneath the curve has to be equal to 1. More of the results have to be clustered around the mean than in the outliers. So there's a higher probability of getting one of these results around the mean than there is of getting a result that's far away from the mean. So that's basically it. We have to have, the average of the random variable needs to be in the middle. The average value needs to be in the middle. The probabilities are evenly distributed on either side of the mean, and more of the results, in other words, the greater probabilities for results occurring this should be higher around the mean and lower along the outliers. Now, this is a good example. This graph on the left is a good example of a probability distribution with high variance. And over here on the right, we have a better example of a probability distribution with low variance. What does that mean? Well, high variance means high standard deviation. It's the same thing. Means that we actually have a greater spread. So there is more distributions, kind of like away from the mean. Over here, things are clustered pretty tightly around the mean, but these are still both normal distributions. We can still work with these. Also, most curves that are approximately normal are going to work for our purposes in terms of making determinations using things we know about the normal distribution, which we're going to get to in a second. So I'll go ahead and open up a new page, and I'm going to go back to black. So much for that. Back to black. Here we go. Something that looks a little bit like this. Well, yeah, that's going to work. We're a little bit off center, but and it seems like there's a longer tail off to the right than to the left. This is called it skewed a little bit to the right. That's going to be fine. It's not. We're not too far off. Actually, let me begin with the horizontal line. This is going to make things easier on me. Even something that looks a little bit like, well, yeah, we're getting. This is probably going to be okay too for our purposes. That's going to work as a normal distribution. Stuff that won't work, if we have that's hardly horizontal. Just bear with me, folks. I'll get it together. Something that looks more like that. Not a normal distribution. We can't work with that. And certainly something that looks like this are not going to work for our purposes. So the important point I want to impart here is that a curve does not have to be exactly normal. In fact, when you're talking about sampling, when you're going to take 100 results, it's never going to be exactly normal. But if it's kind of close to being normal, which in many cases is going to happen, it's going to work for our purposes. We're going to be able to determine things using the standard deviation and be really close to spot on with our predictions. So, well, it's when we get down here when we have massive skew. This would be a massive skew to the left where the long tail goes out here and we have very few results over here. That's not going to work, nor is something where we have more than one peak. So, why are normal distributions important? Let's talk about that. I'm going to go ahead and open up a new page just so we're looking at a fresh new canvas. Normal distributions are important. First of all, because they happen in nature all of the time. So, if you measured a whole bunch of people's heights in the population, if you took a whole bunch of women's heights in the United States, what you're going to get is you're going to get an average and you're going to get a normal distribution around those heights. You're going to have some outliers. Some women are going to be far away from the average. They're going to be very short or very tall. But for the most part, if the average height of women in the U.S. is about 5'6", a lot of women are going to be sort of between 5'4" and 5'8". And then there's going to be some outliers. So you're going to get basically a normal distribution. Same thing goes with, like I said, scores on tests. The IQ test is a great example of a normal distribution, as is the SAT. This is a really important one. Measurement errors. I mean, this could be thought of simply like if you took out a tape measure and measured a wall. Sometimes you're going to be pretty close to the wall has some empirical length. You know, there's some length associated with that wall that is true. But if you take out a tape measure and you're measuring that wall, sometimes you're mostly going to be around the correct measurement for the wall. But sometimes you're going to be a little bit less. Sometimes you're going to be a little bit more. Especially if you have to like mark, if your tape measure is not long enough, you have to mark a spot on the floor and then extend it again. You're going to be a little bit off. And you're going to be off by small amounts most of the time. And occasionally, you're going to be off by larger amounts. And it's going to be you're going to have an even distribution around the actual length of the wall. So your measurement error, sometimes it's going to be negative, sometimes it's going to be positive, is going to look like a normal distribution. Also hugely important, and I'm going to get to this later, is something called, we have this thing called the central limit theorem. And that says, I don't want to, if this is confusing right now, don't worry, I'm going to explain this a lot. You may have heard of this elsewhere, but we're going to be talking about this a lot later, is the central limit theorem. The central limit theorem says, when you start sampling from a population, so you're taking, you've got maybe a huge group of people, that's the population, or a huge group of results, that's the population. You start sampling from that. The average, if you take a lot of samples, the average value of those samples is going to follow a normal distribution around the average of the entire population. So you're going to get, sometimes your sample is going to have an average that's a little bit less than the average of the population, and sometimes it's going to be more than the average of the population. But most of the time, most of the results from those samples are going to be clustered around the actual average of the population. And very occasionally, you're going to get outliers on either side. You're going to take your sample of, say, 1,000 values, and if you did 1,000 samples of say, well, let's say 100, you're going to sample 100 people, and you're going to do 1,000 of those samples, the average of each of those 100-person samples is going to be around, it's going to be a normal distribution around the average of the population. Don't worry if that's confusing. We're going to talk a lot more about that later. So, really very important for our purposes, another reason why normal distribution is so important is because it tells us so much about the distribution of the population, because it's very predictable. If we know the average and we know the standard deviation, we can say a whole lot about the probabilities of things happening with those results, with those what the probability of certain outcomes are for the random variable, if we have the average and if we have the standard deviation. So, for instance, we know that, and I'm going to get into this a little bit more later, but we know that within one standard deviation, plus or minus one standard deviation, 68% of our results are going to fall within one standard deviation. So from -1 to +1 around the mean. We also know that 95% of the results are going to fall between two standard deviations of the mean. And within 3 standard deviations of the mean, that's going to be like 99, I may get this wrong, it's going to be something like 99.7% of the results. So nearly all the results are going to fall within 3 standard deviations of the mean. It's going to be very rare for you to have an outlier that is more than 3 standard deviations from the mean in either direction. For all normal distributions, this is universally true for normal distributions. So it doesn't matter what the standard deviation is. The standard deviation can be large or it can be small. What we're talking about is in terms of the number of standard deviations from the mean. In fact, there are tables that will show you exactly what percentage of results you can find within a certain number of standard deviations. Let's take a quick look at that. This is called a z-table, and we're going to talk more about z-tables later on. But what it basically shows you is Down the left side and the top, the left column and the top row here, we've got z-scores. This is the number of standard deviations we are from the mean. So we might say, negative 0.5 standard deviations from the mean. And it shows what percentage of results are going to be that number of standard deviations or less. So you can see at 0 standard deviations from the mean, it's going to be 50% of all results are going to be less than or equal to 0 standard deviations from the mean, because that's just going to be equal to everything to the left of the average. And so, there's always going to be 50% of the results on either side of the mean. So that table will give you everything. If you know the standard deviation, you know how many standard deviations you are from the mean, and you know the mean, of course, you can tell exactly what percentage of results are going to fall within that range. Let's look at a simple example, and we're going to do this a lot more. We're going to talk about the z-table quite a bit more in the next video. But let's take a simple example. Every year, thousands of students who are thinking about business school take the GMAT. And the GMAT has a normal distribution in terms of its scores. It has an average of 540 and a standard deviation of 100. So, a couple things about the normal distribution, standard deviations. I've mentioned this a couple times, but within one standard deviation of the mean, you're going to have 68% of all results. Within 2 standard deviations of the mean, you're going to have 95% of all results. So let's do a normal distribution. It's always a little bit of a challenge for me to draw these. Hey, that went pretty well. I'm going to do another one here. That's about as good as you're going to get from me. I'm pretty proud of that, actually. So these both show the distribution of scores on the GMAT. We have an average of 540, and since there's a standard deviation of 100, plus or minus 1 standard deviation is going to be between 440 and 640. Between 2 standard deviations is going to be 340 and 740. And as I just mentioned, within 1 standard deviation is going to be equal to 68%, and within 2 standard deviations is going to be 95% of all results. So of all the people who take the GMAT in a given year, 95% are going to score between 340 and 740. 68% are going to score between 440 and 640. So here's a question for you. If you scored a 640 on the GMAT, what percentage of people scored less than you did? All right, so essentially, what was your percentile score? What percent of people scored below you? Let's think about that for a moment. I'm going to draw a whole new curve here. We know that the average score is 540. And your score is over here. It's 640. Okay, it's not entirely consistent with the way it looks up here, but that's just because I'm drawing this by hand. So your score is here at 640, and this is also known as plus 1 standard deviation. How many people did you do better than? What percentage of people did you do better than? Well, we just said, if this is 440, then the area in the middle, this is going to be equal to 68%. And what does that mean? It means the areas on the sides together have to equal 32%, right? The people who scored better than 640 and worse than 440, that has to equal 32% because it's the complement of the area in between 440 and 640. So 32 plus 68 is equal to 100. That means that because the normal distribution has an even spread on either side, this is going to be equal to 16%, and this is going to be equal to 16% as well. Furthermore, on either side of this curve, this is going to be 50% of all results, and this is going to be equal to 50% of all results. So if you're over here at 640, you know that 16% of people did better than you. Therefore, 84% of people, that's 1 minus 16%, are going to have done worse. So all of this is going to be equal to 84%. In other words, you scored in the 84th percentile. Another question. So still dealing with GMAT scores. Average is 540, standard deviation is 100. I'm going to open up a new page. What percentage of test takers are going to score between 440 and 740? Whole new curve here. Think about this one on your own. In fact, if you'd like to pause the video and figure it out for yourself, what percentage of test takers scored between 440 and 740? I can't tell you how pleased I am with my curve drawing. This is really, I'm normally kind of a disaster that looks lumpy and, okay. by now you know my handwriting is not terrific, so I'm pretty pleased with the curves I've drawn in this video. So here we're looking for the number that fall between 440, that is between -1 standard deviation, and 740, that's +2 standard deviations, right? This is getting a little bit tricky. Well, we already knew that to go between 1 standard deviation and 2 standard deviations, that's going to be 68%. And we can further break this down to say between -1 standard deviation and the average, it's going to be half of 68%. It's going to be half of 68% over here, half of 68% over here. So that's equal to 34% right there. Now what about this 740? Well, we said between the 95% of all results are going to fall between -2 standard deviations and +2 standard deviations. When you have, our standard deviation is 100, and so we said we know that 95% of all results are going to fall between 340 and 740. So that must mean that out here, if I write 340 over here, out here on the edges, these are going to add up together, are going to add up to 5%, right? Because 95% of all results are going to fall in between 340 and 740. Therefore, this right here, just this, is got to be equal to 2.5%. Half of 5%. So, bear with me. We know that on this side of the average, this is 50%. And this little area right in here is 2.5%. So what's this area in here? Everything between the average, 540, and 740, 2 standard deviations, well, it's going to be 50% minus that little outlier piece, everything above 740, which is just 2.5%. So this area is going to be equal to 47.5%. Now, we're there. We've got 34% falling between the average and -1 standard deviation, plus we've got 47.5% falling between the average and +2 standard deviations. So we just have to add these two together. So this is going to be equal to 81.5%. So 81.5% of all results are going to fall within 440 and 740. In our next videos, we're going to look at a lot more examples of the normal distribution, and we're going to talk about looking when we don't have just exact numbers of standard deviations. We're going to go back to the z-table and start figuring out how we can what kind of percentages fall within ranges when it's not a whole number of standard deviations.